What's up, class? This is our fourth online lecture. In this lecture, we will go over exponential growth and decay. For those of you who were here last week, we kind of went over this a little bit algorithmically, but in this lecture, we will go over it contextually and also continue to solve a few problems so that we can do well on our review assessment and crush our practice. So let's take a look. Let's say, for example, we have two patients. Let's say you're a doctor, a scientist, whatever the case may be, and you are trying to figure out why patient 1 is growing in white blood cells and patient 2 is decreasing in white blood cells. So let's take a look at patient 1. For patient 1, it seems to be the case that after 1 hour has passed, right, which is what we are charging this exponent to, is t. Let's say that after 1 hour passed, they had 2,000 white blood cells. After 2 hours passed, they had 4,000 white blood cells. Well, 4,000 is double 2,000. We know that to be the case because 2 to the power of 1, or 1 hour, would be 2 times 1,000 is 2,000 white blood cells total. So if we graph that coordinate point, that'd be somewhere here. And let's say that after 2 hours, 2 to the power of 2 is 4 times 1,000 is 4,000. That's somewhere up here. Then let's say that after 3 hours, 2 to the power of 3 is 8 times 1,000 is 8,000. That's somewhere way up here. So if we were to graph this, it would look something like this, right? Exponential growth. Now what about this patient? This patient starts off with 8,000 white blood cells, and it seems to be the case where their white blood cells are being chopped in half over time. So let's figure out why this is the case. So after 1 hour has passed, 1/2 to the power of 1 is 1/2 times 8,000. 8,000 divided by 2 is 4,000. Let's say that after 2 hours have passed by, 1/2 to the power of 2 is 1/4. 8,000 divided by 4 is 2,000. So again, that's somewhere down here. And let's say that after 3 hours have passed by, 1/2 to the power of 3 is 1/8. 8,000 divided by 8 is 1,000. So we cross by their predisposition first, and then it just seems to be the case where they are decreasing over time. So what do we notice to be the difference between these two equations? Well, their predispositions are different, but something else is also different. It seems to be the case that their base values, which is the value to which the exponent is being put to, it seems to be the case that these are different as well. Well, these two values are actually the ones that are influencing whether or not there is exponential growth or decay occurring. Let's figure out why. For exponential growth, if our base value is greater than 1, we are growing. For exponential decay, if our base value is between 0 and 1, we are decaying. Let's further take a look at some problems to substantiate this claim. What I like to do first is always draw my x and y values. So we have 1, 2, 3, 4. 2 to the power of 1 is 2, to the power of 2 is 4, to the power of 3 is 8, to the power of 4 is 16. Let's notice the pattern. To get from 2 to 4, I have to multiply by 2. Same thing to get to 48, same thing to get to 8 to 16. We would call this a doubling sequence. If I were to graph this doubling sequence, what it would look like is something like this, where I have at the power of 1, I am at a value of 2. To the power of 2, I'm at a value of 4. To the power of 3, I'm at a value of 8. To the power of 4, I'm at a value somewhere all the way up here at 16. So, what would our predisposition be if we do not have a value out front? What would we assume it to be? Well, we would always assume it to be 1, because 1 times any number is that number. So 1 times 2 is 2. So in fact, our predisposition is somewhere right here at 1. Let's graph this. This in fact looks something like this, exponential growth. Let's take a look at an exponential decay problem. Again, let's write out our x and y coordinate points. 1, 2, 3, 4. 1/3 to the power of 1 is 1/3, to the power of 2 is 1/9, to the power of 3 is 1/27, to the power of 4 is 1/81. Let's figure out what this will look like if we graphed it. Again, 1/9 is less than 1/3, 1/27 is less than 1/9, and 1/81 is less than 1/27. So we said that when we were at the power of 1, we were exactly at 1/3. To the power of 2, we were at 1/9. To the power of 3, we were at 1/27, and to the power of 4, we were at 1/81. Again, our predisposition would be the same thing. It would still be at 1. So that's somewhere up here. So let's again draw our decay. That's what this will look like over time. Exponential decay. Let's look at one more problem. This problem's a little bit different. In this problem, it seems to be the case where we are adding an additional 1 to the outside of this function. Well, what is that doing? All that is changing is, in fact, 1, it is changing our predisposition, because we will additionally append by 1. And then it also changes how our minimum is behaving. So let's take a look. Let's say we put out our coordinates. If we have 1/2 to the power of 1, that is in fact 1/2 plus 1 is 3/2. The power of 2, that is in fact 1/4 plus 1 is 5/4. The power of 3 is 1/8 plus 1 is 9/8. And then to the power of 4 is 1/16 plus 1 is 17/16. If we were to graph this, we in fact have our, up here we have our 3/2. Here we have our 5/4. Here we have our 9/8. Here we have our 17/16. Right? And it would still be a different case. For this, what I will be noticing is that we are slowly getting closer to 1. So at 1, we would call this a horizontal asymptote. All right? And so what this will look like graphically is that, again, at the value of 1, I am at 3/2. At the value of 2, I'm at 5/4. At 3, I'm at 9/8. At 4, I'm at 17/16. So what I am doing here is, again, I'm just simply getting closer to 1. Now, where would I be crossing the y-axis on this one? Oh, 1/2 to the power of 0 is 1. 1 plus 1 is 2. So, on this function, at the value of 2, that is, in fact, my predisposition. Again, because wherever I cross the y-axis, my x value has to be 0. So just plug in 0 for x and solve. So that would be 2, so I would cross that 2 first, and then I'm slowly approaching 1. Now, what would that mean contextually back at our first example? Let's say, for example, we were to add an additional 9,000 white blood cells at the end of for patient 1. So now their predisposition, if we think about it, is 10,000, because 2 to the power of 0 is 1, and 1,000 times 1 is 1,000, plus 9,000 is 10,000. So in fact, here it is 10,000. And then we are in fact doubling that, so that would be 20,000, this would be 40,000, this would be 80,000. All right, so that would be the change. Now what would it mean for decay? For decay, if I added another 9,000 white blood cells, what that would look like is that from my 8,000, I would simply be appending up to 17,000, right? Because 1/2 to the power of 0 is 1, times 8,000 is 8,000, plus 9,000 is, in fact, 17,000. So that would be 17,000 as our predisposition. We are, in fact, cutting that. That would be 13,000. We are, in fact, cutting that, which would, in fact, be 11,000. Let me see, yes. 11,000. And then here we would be slowly approaching 9,000. So again, we would never approach 9,000. So we would never fully be 9,000 here. And for this, 9,000 is somewhere down here. And this would be our starting position. Right, so this one, we're starting from 10,000 and we're increasing. And for this one, we're slowly approaching 9,000. So if you need any additional help with any of these problems, please reach out to me. I would love to converse further about exponential growth and decay. Feel free to email me or feel free to send me a Canvas message. Either one would be perfectly fine. I will make sure to get back to you as soon as I can. Have a great day.